Thank you for coming along. Hope you're all suitably fed and hydrated and ready to listen to us talk about getting paid, but also getting paged. So, who are we? I'm Miles. I'm a senior staff engineer and platform at Monzo, working on infrastructure platform, looking after compute, networking, observability.
And I'm Dom. I'm a staff engineer inside the same squad Miles just mentioned, so all the same stuff.
And we work at Monzo. Who has heard of Monzo? I'm glad there are a few Monzo people in the audience who put their hand up, so that's a good start. We're a digital bank. We have 40 million customers in the UK, business, retail, etc., etc. We have a product in the US that's growing, and we are just about to start expanding more internationally to the EU, which is exciting. But one of the fundamental features of a bank is letting you get paid by your employer, which is pretty important, right? And in the UK, one of the main ways that this happens is via a payment scheme called BACS, which stands for Bankers Automated Clearing System. And this powers lots of scheduled payments. So it might power things like your gym membership or your utility bill via direct debits, but it also works the other way with direct credits, which are used for salary payments. And this is broadly how BACS works. It works on a 3-day timeline, right? So on day one, your employer is going to run your payroll, work out how much you should be paid, and send that off to their bank. Their bank is then going to send that to BACS, and BACS, by the next day, is going to forward that on to Monzo and say, please credit all of these people their salary. And then normally what happens on day 3, all the money sort of moves around, it settles, gets credited into people's accounts, and everyone's happy, right? But one of the really interesting features of this system is that if someone makes a mistake, if the payroll's wrong, then the source bank can actually ask BACS to cancel the credit and say, please don't pay this person, we've made a mistake. But the deadline for that is actually at 3:30 p.m. on day 2. And past that point, we basically know how much everyone's going to be paid. So we thought, why wait till the next day? Why not just give people money then? And we built this feature about 6 years ago or so. Pretty nice. You open the app, you have this lovely little animation, you drag it down, and you get your money straight away, instead of having to wait sort of overnight and wake up the next day. And we decided, well, we know what people are going to be paid at 3:30 p.m, so let's make it available at 4 p.m. on the dot, every single day. Can anyone think of any potential issues with inviting all your users to open their app and receive money at the same time every time they get paid? Yeah. Turns out, we found out pretty quickly within the first month of building this that, people really like getting paid, doubled our edge traffic, we'd not scaled up our systems at all, and that did not end well. And we thought, well, what are we going to do here, right? We could roll back this feature, we could go back and figure out how to build it more safely or whatever, but it's a really, really good feature. People really cottoned onto and really liked this feature straight away. And we wanted to work out how we could sort of roll forward and deal with all of this extra load. And that's what we're going to talk to you about today. I'm going to take you through our journey from Payday Pandemonium to Salary Serenity. And we're going to dig into lots of different strategies that even if you're not a bank, you can use for any sort of load events that you might have. But first, I'm going to hand over to Dom to talk a bit more about our platform environment.
Yep, thank you. So we're just going to set some basic background of what our platform looks like. So when we're talking about things, it's in context. So to start with, Monzo's architecture. This is not a very detailed diagram, you'll note. But at a high level, we run in a single AWS region, EU West 1. Didn't go down the other day. We run a EKS cluster, and on the EKS cluster is a range of workloads from our microservices. There's about 3,000 or so and counting. We've got our observability stack, so that's profiling, tracing, monitoring, metrics, and logging. We then have Kafka clusters. We run 3 main Kafka clusters that sort of power the bank and the various systems that go there. And then we've got other components around the edge. This is everything you'd expect for a working Kubernetes cluster, from load balancer controllers to metrics exporters to everything. We then have a range of AWS services we use as well. We don't use too many of these, but we have S3 for our blob storage. We've got key spaces for managed Cassandra. We actually give each microservice its own key space if it wants it. And then we also run etcd clusters on EC2 nodes outside the cluster. We've got about 6 or 7 of these clusters currently running. Jumping into Kubernetes specifically, it is KCD. We have a set of node pools that Carpenter is managing. We have some that are both spot and on demand for our microservices as a whole. We actually run like 90% spot nodes and various other components that run on them as well. I actually gave a talk last year, more details about Carpenter if you wanted to hear that, just a self-plug. We then have on-demand node pools as well to run things that don't handle spot toleration, like spot terminations. If you've got 2 minutes notice, you don't want your metrics ingestion or your Kafka clusters to be killed very quickly. So they run separately on node pools that have slow drift and management there. We then also expose pods directly with using load balancers. So we've got NLBs and ALBs exposing the pods. So when you hit the endpoints in the app, you're hitting load balancers, which are just hitting pods on our edge, and then that goes into all the microservice traffic from there. One layer deeper then, we've got microservices. Now, microservices are a contentious topic sometimes, and I think people a lot of the time picture 10 different languages, 10 different database stacks, and all sorts of things powering the microservices. We have a single database that we use, which is Cassandra. We write 95% of these microservices in Go, and all of the interactions with like third-party and common components is done via libraries. Us in the platform team write and manage these libraries. So if someone talks to Cassandra and someone talks to Kafka, it goes via abstracted libraries first, then we can actually control and manage that at a platform level. We then have Envoy deployed as well for our service mesh, so all service communication goes via these Envoy MTLS connections, and that's running a mesh that we write and manage ourselves. So back to get paid early now. The question really is, why is get paid early so bad? And like, why do we have these sort of problematic DDoS events that form? So when people get paid, you get peaks throughout the month. If everyone, who here gets paid in the last like 5 days of the month or so? Nice, we had hands up. That's more than a sixth of the thing. So people get paid normally at the end or the start of the month, and that doesn't distribute evenly throughout the month. What this means is all the paydays will group up together, and then because of the back system, where it's only on business days, they'll group up even more. If your payday lands on a weekend, then you'll get paid on the Friday instead. Lastly, we have bank holidays, which then also cause more grouping up. Bank holidays are pretty much always Mondays or Fridays, so it causes further people's paydays to get together. This is more notable with things like August bank holiday, for example. That's at the end of August, and then we've also got like bank holidays in Easter that move around as well all the time. So the Easter bank holiday next year is actually forming at the end of March. So we have a 6 or 7 day payday all at one happening at once. If there's an incident, then I'm on holiday. It's not me. Now, the other thing about get paid early that makes this worse is 4 p.m. is the time when most people in the UK are awake. They're not asleep, which is what normally happens when you get paid. If you have a payday and you get paid whatever time happens in the morning when the back run goes through, you don't wake up to get paid. You will wake up gradually throughout the morning as your alarm goes off and maybe do a bit of banking when you wake up as that money comes in. This is actually our edge proxy graph showing the amount of traffic that we get during the morning. You can actually see people's do not disturb and alarms going off. So every half an hour you get these peaks. This is quite nice because if you're a horizontal pod autoscaler, you can scale for this quite easily. You're not getting these massive surges that are suddenly happening. And as people wake up, they do more banking stuff, and we can slowly, gradually ramp up and scale out our platform throughout the day. And here's what happens at 4 p.m. This is a graph of our edge proxy traffic showing the amount of requests a second we get. This was from about 2 months ago on quite a large get paid early. And you can see our edge requests went from about 20,000 a second to nearly 50,000. This spike actually looks a bit better than it normally is. This spike is in the space of a minute as well. So the amount of traffic hitting services in a minute is rocketing up. Now, this isn't actually traffic driven by us. This is just customers going, oh, it's 4 p.m. I'm meant to get paid. I'm going to open my Monzo app and try and get paid. And as you can expect, this causes a lot of problems, particularly back in 2019 when we had no horizontal auto-scaling whatsoever. The other edge of this is we get, say, 20,000 extra requests a second on our edge. What that actually translates to across all our microservices in our service mesh is about 10 million requests a second for all the services. If you think a single API call to load your feed might actually be 300 sources of information and RPC calls that gets made. So you can see how the amount of traffic that ramps up in the space of a minute really hits our platform. Now, what happens when this goes wrong? Well, we have a set of cascading failures that occur, and I'm just going to talk through a sort of a single service example here. This graph is showing the amount of memory a service uses when it gets overwhelmed. The red line is showing memory spiking up, and then the red dotted lines are annotations when they had out-of-memory kills. This isn't actually too bad. We have a few pods that are crashing, and overall we can handle the amount of retries we need to basically avoid it causing too much of a problem. This is the amount of requests coming in and the error rate for those requests, and you can see that we actually only got about 5 requests erroring a second during these out-of-memory kills. This looks fine. The problem is what happens upstream. Now, a pod talking to another pod has connections, and we use long-standing HTTP2 connections. That's because MTLS connections are quite expensive to initiate, so we basically reuse those to avoid having latency when we're setting up those new connections. When the pod goes down, we have to set up a lot more of those connections, and we have to have retries in the service mesh. So the cascading failure of a single service actually means that all the upstreams have increased latency, increased memory usage, and they can also fail, causing even further cascading across our microservices. So how do we fix this? How do we prevent services from being overwhelmed from sudden spikes of traffic? Well, back to Miles.
So clearly we have a problem here, right? We have too much demand with too many requests per second, and we don't have enough supply of service CPU cycles or memory to service it. So what did we do? Well, in the beginning, as Don mentioned, we didn't have horizontal autoscaling. We just had statically set scale per service. So the very first thing was obviously just to scale things up. And we did this initially just manually, reactively in the instant. We go, okay, which services are crashing, which are under lots of load. Just write this list and then go through them one by one and scale. Like no magic or fancy automation, just do it. And then we decided to be a bit more proactive about it and start reusing the same list, scaling up the same services. But we wanted to get a bit more confidence that we were scaling the right services, and when we came to the next get paid early, things would actually work. And to do this, we did load testing to kind of simulate what might happen during a get paid early. I think load testing can be quite tricky with a complex product like Monzo. It's not just a single API endpoint that you can just point a off-the-shelf tool at and just like ramp up the number of requests. You know, when you open your app as a Monzo user and load the feed, there are tens or hundreds of API endpoints the app is going to be calling to actually fetch that information and display it. So we really wanted to try and simulate as faithfully like the journey of a user opening the app at Get Paid Early. So we wrote our own load test worker for this that kind of ran through that journey and hit these endpoints. And we built our own kind of simple orchestrator that could just spin up lots of these workers and like hammer our API. We could do our scaling and see whether it actually kind of worked and adjust from there. Now, this was fine for a while, right? While we were getting started, but we quickly ran into some of the problems with this approach. So the first issue is that Monzo is a moving target, right? Constantly developing new features, new products. Like a few weeks passed, and there are more products and services that are on the app load hot path. And it only takes one of those services to appear that we haven't got on our scaling list, and suddenly, no matter how much load testing we do, the next get paid early, that service might fall over and cause a cascading failure. This process also took so much time, right? We were probably spending up to about 2-3 hours a week just scaling and load testing and doing all of this. And it's not particularly glamorous work, but it's also like time we can't spend on actually building features and improving Monzo. And also like doing things manually, as we all know, people make mistakes, and yeah, we decided to make it better. So one of the first things we thought of doing is, actually Kubernetes has a built-in tool for this, right? Which is the horizontal pod autoscaler, which does what it says on the tin, Like you give it some input and it adjusts the number of pods for you. Now in our case, we figured that our main constraint is CPU. We receive lots of HTTP requests. The services have to do CPU work to service those requests. So more requests, we need more CPU. So we target about 70% CPU utilization. And the HBA works well for reacting. It's pretty fast. It can spin up a bunch of pods in under 30 seconds. But it still takes time for Kubernetes to actually spin up those pods. So we needed something else. In particular, if we try and add 100 or 200 pods to our cluster, and our cluster doesn't actually have the capacity to schedule those pods straight away, then we have to wait for those new nodes to come up, and that can take a bit of time. Even like we're using Bottlerocket and EKS, find it spins up really, really quickly, but it still might not be quick enough. So one thing we did was to reserve space in the cluster kind of proactively. And the solution we found for this was just to run a simple deployment that just runs the Kubernetes pause container, it just runs idle all the time. We can reserve the resources, and they can just sit in the cluster, taking up space. But the key bit is that we use the priority class feature of Kubernetes we can set the priority really, really low. And then whenever an actual real service pod that we want to schedule comes along, Kubernetes can actually evict these from the node, schedule the real pod, and we can spin it up really, really quickly. It just basically allows us to keep lots and lots of headroom around. And the other thing, as I said, is we'd started doing more proactive scaling and starting to scale services up before 4 p.m. because obviously we know exactly when this this load spike is going to happen. We're quite privileged in that respect, and this allows us to just make sure we've got enough supply of service CPU cycles when that hits. And we started off doing it manually. Then we moved to automating it and building a system that would generate a plan for the services we needed to scale, and then actually run through the plan and scale up each service individually before 4 p.m. And needed to do a few checks while doing this to make sure we didn't overwhelm the cluster, allow people to still deploy things normally to the cluster. But even so, doing it slightly slowly, we can scale these whole thing in less than an hour. But the really interesting part of this system is actually how do we know how much to scale services up by? Like I said, people are adding new services and new endpoints and things all of the time, which are just constantly going into this kind of app load hot path that we care about so much. And one of the things that we found really, really worked for us was actually using our tracing data, using kind of Jaeger and OTel. And this actually allowed us to look at the endpoints that are on the app load hot path, get a list of all of the services that were being called by that, and say, okay, we know we need to, this is the list of services that we actually need to scale. We could also use some other inputs like previous get paid early peaks and metrics from services. We could compare how much CPU each service had, how much the HPA had to scale up the service by, and use that to inform the plan for the future. And the other important thing of this was, of course, scaling back down afterwards. We didn't want to just leave our system scaled up all of the time, cost money, waste resources. And we found for this, we could just reverse the process and drop the number of minimum replicas in the HPA. And then the system would sort of naturally scale down over time as the user load sort of tapered off into the evening. And then we find that a cluster autoscaler just scales in the nodes. So back to Dom to talk about shedding load.
Yep, thanks. So we've talked now about how we can scale up things to handle the big spike of traffic coming in, but what about what we can do to actually just reduce the spike of traffic itself? Load shedding at Monzo had quite small beginnings. We basically had some people during incidents who were like, here's a useful thing I did last time that avoided some load, and it was just grown fully out of incidents. We'd have incidents, we'd type in the channel, we think we should just turn this thing off, and someone has the expertise to know it's not going to break everything. And we basically had this set of tools that we could use to reduce the load on our platform. Over time, obviously, word of mouth incident and relying on a single person to be in an incident who knows what to do isn't ideal. So we sort of built this into a set of runbooks. We've had quite a few incidents at this point, so this runbook went to about 40 different load shedders that we could have. These were all written down with a set of manual steps for how to operate them, whether it be turning off config or scaling down something. But these all were written in a way that we knew it wasn't going to impact customers. We could turn this thing off, and it's not going to actually change the customer experience in the app, which was the key thing here. We also rated what the load shedders were by the level of customer impact they'd have, so you'd know if it was going to have no customer impact or major customer impact, major still being better than the entire bank goes down, which doesn't happen. Then, to sort through some of the load shedders, To talk through some of the load shedders we had, a key one is disabling unimportant background asynchronous tasks. As you can imagine, think through your own environments. There is a lot of things that run in the background that don't need to be done in real time. One thing notably for us is our analytics pipeline. We don't need analytics events to be shipped the second they're produced, so we can allow them to back up on a queue. They're just going to wait there on Kafka, and then we can process them later. We do quite like them to be recent, so we do actually process in near real time constantly. But when we have large get paid early peaks, we can basically rate limit the processing of those, reduce the amount of traffic that those analytics event processing and enrichments are causing, and we can reduce the load on our platform to sort of lighten the load and make sure we're not going to be overwhelmed. There's other background tasks as well that don't have to be processed in real time, like our batch iteration jobs and MasterCard clearing, and these basically just mean that we can hold off processing in the 10-minute peak that get paid early is going to hit. The other side of this is we can actually cache information. Now, as a bank, we don't really want to overuse caching because the whole benefit of Monzo is you see up-to-date real-time information. You spend £5 at the pub and then you see that money go out of your app right away. If we were caching that and we were like, oh, we're not going to tell you for an hour, that wouldn't really be an ideal user experience. So we want to use caching sparingly. We found, however, that some endpoints could be cached without having any customer impact or very minor customer impact. These are ones where when you get a push notification to your phone, we actually preload information in the background for you. The idea being we can have some information loaded in the app, so the app loads quicker when you open it up. Instead of having this data load, we just cache the data from these push notifications, and this meant we could actually reduce traffic from those by about 5%. This graph is actually showing the amount of traffic we were caching during a recent get paid early, and it's all of the non-green lines. You can basically see that about 5 to 10% of our traffic we could cache without anyone knowing we're caching it, and we could avoid all that load hitting our downstream systems. This gets turned on during most large get paid earlies, and we basically have thresholds for how large those are and if we're going to turn them on or not. What we found over time, however, with our load shedding runbooks is manual processes aren't great because they rely on humans that have to run them, and humans can make mistakes and forget to run them or forget to turn them off sometimes. So instead, we built another microservice to run the load shedding for the rest of the microservices. This service is called the load shedder, and it sheds load. It basically is the runbook, and it's just automating all those steps in the runbook that we know have worked and have been tried and tested in an instance before. You can easily call this load shedder just making an RPC request in the CLI to say, enable this set of load shedding, and anyone at Monzo can run these, and anyone can do them easily. The idea being that anyone responding to an incident doesn't need to page platform. They can just say, oh, platform's being overwhelmed by load. Let's start shedding some no custom impact load here. Again, these have the levels of customer impact as well. So someone just knows that if I enable level 3, customers might notice, but if I enable level 0, no one's going to know it's actually on. Lastly, we thought, how can we actually change get paid early, the product? As we mentioned, we don't want to just say in platform, no, you can't have get paid early as a feature. Customers love it. So many percentage of customers actually get paid early each week. And if we turned it off, people wouldn't be happy, and we don't want to have platform deriving the features that we can offer. So instead, we can actually change what get paid early does to make it just a bit lighter on platform. The first get paid early, what happened is at 4 p.m. on the dot, we sent everyone a notification if they were eligible saying, hey, come get paid. As you can imagine, not just everyone coming to the app at 4 p.m., but telling people to come to the app and sending them a notification causes lots of load on the platform and causes lots of issues. Now you can see this graph on the right showing we actually send out notifications half an hour later, and we send them out over an hour period, so we're not overwhelming our platform at once. The funny thing with this is customers want to get paid at 4 p.m. on the dot still, so even without a notification, they're still opening the app at 4 p.m. This rate limiting has been in place for years now, and we still have an edge proxy graph that triples when get paid early hits, but I imagine it would be worse if we hadn't have done this. The other thing we can do is actually delay processing of get paid early payments. So you might have seen on some very large get paid earlys this message in your app that says your money's coming soon. This is only like a 1 to 2 minute wait, but by rate limiting the amount of payments we process, we can reduce the load on downstream systems and control it. So it's not just driven by customer behavior, but we also have platform levers we can control to lower the rate of payments as well, which is very useful. So back to Miles on what's next.
So our journey has been pretty successful. Like 5-6 years ago, the really big get paid early peaks were always a terrifying kind of see in the morning the size of the peak, and then go right. What are we going to do? Let's go and like shed a load of load and scale things. Whereas now they're pretty much non-events. They just happen all the time. We don't really have to think about it. Occasionally, there's a small issue, but it basically works. So what do we want to do next here? One thing is on our current scaling system. It works fine. It's basically a bunch of code with heuristics, which is quite challenging actually to iterate on. If we want to make improvements, we want to change how it scales, it's quite tricky. But really, this is a sort of data and ML shaped problem, right? We have a bunch of inputs. We have previous service scaling data, get paid early size, etc., etc. We should be able to train and iterate on a model offline that produces kind of nice scaling plans. And this is one way that we could make scaling more efficient and cost effective over time. We also want to look at the scaling part of the system itself. And instead of having our kind of hand-rolled services that interact directly with the Kubernetes API, we want to look at things like Payday, like where we could integrate the horizontal portal to scaler with maybe a custom proactive scaling signal from our plan generation, and just have one system doing all of the scaling. To wrap up, a few takeaways. So first thing is minor product decisions can have very outsized long-term impact on user behavior. It seems really, really obvious to see that now, that if we let people get paid at 4 p.m., everyone's going to want to get paid at 4 p.m. But it wasn't necessarily so obvious at the time, right? We didn't know how popular this feature was going to be. We've also spoken about a bunch of strategies, reactive auto-scaling, proactive auto-scaling, load shedding, etc., etc. I think one of the more general takeaways as well is that you don't necessarily need to kind of solve the world up front and try and magically automate everything. It's fine to just start manual with a few kind of small steps, and then build on that as you see that success and wins from doing those small steps, start automating things and move on to the next thing. And I think finally one of the most important things that's really helped us through this journey is making sure we use our instance as like a primary learning opportunity for improving our system. Like instants happen, they are expensive lessons. It makes sense to get the most out of them as you can, kind of run postmortems and debriefs and take actions and come up with ideas. And that's it. There's a couple of blog posts we've referenced. We'll leave the links up there. But otherwise, thank you so much and enjoy the rest of your day.